I would like to talk about our latest development for crystallization furnaces for silicon. And first of all, I will give a quick overview about the technical details of the so-called STU 650. Furthermore, I will show some achievable product qualities, and I will finalize my presentation with an overview about the achievable cost of ownership with this new machine. Here we see the technical description of our STU 650. We have a water-cooled steel vessel. Inside we have a hot zone, a modular hot zone, which is made of rigid graphite felt. We have top heater, side heater, bottom heater, which are independent controllable. And underneath this we have a so-called triple heat gate, which acts as insulation layer. Underneath the triple heat gate we have an active cooling unit to take the heat during crystallization. For runout protection we have a double layer made of copper and massive ceramic, which can withstand all the 650 kilogram liquid silicon. Because heat flux control is a key element for proper crystallization, I would like now to focus a little bit more on the details of our heat flux control. We have, as shown before, we have a top heater, not shown here as a side heater, a bottom heater, and the active cooling unit, which is water-cooled copper plate. And in between, we have the so-called triple heat gate. The triple heat gate is made of 3 layers of graphite felt with different openings, either in the middle or off-center. By this means, we are able to control and adjust the heat flux in whatever manner we want. This means we can have 100% cooling area available. We can adjust the solidification rate in the interface shape, the temperature profile, and this results in a consistent growth rate. The high thermal gradient in liquid metal, which we can apply, helps to prevent any constitutional supercooling. And the side heaters finally help to apply a tailored thermal field, including traveling magnetic fields. By changes of the shapes, we can change the interface shape during crystallization, and so we can have optimized nucleation and growth behavior. This I would like to show you now with the first example, the center heat gate, center triple heat gate. As you can see, we have the openings in the middle, and during the crystallization, step by step, we remove the slides. And then you get a central heat flux from the top down to the cooling plate. And this results in an interface shape which is pretty much convex. As you can see here, the ingot height versus dependent on the crystallization time for a center position, the red line, and for an off-center position, which is about 300 millimeters away from the center line. And as you can see, during the crystallization, more and more, we achieve a convex interface curvature with up to 20-25 millimeters curvature. For sure, we can also do the opposite. This is for the inverse triple heat gate, where you see the openings are at the outside, so we have an outside heat flux. And by this means, we achieve a concave interface, which is also close to minus 20 millimeters. This means in the center side, you have a higher ingot already solidified. Everything with this configuration and process recipe tuning, every configuration for the interface shape between pretty much concave or pretty much convex is possible. This means we can control the crystallization in every manner we want. Now I would like to show you some process data of our SCU 650. We have, as mentioned before, charge rates from 650 kg up to 800 kg. The uptime is more than 97%, which is related to the modular design of our concept. This means the downtime is very, very low. Feedstock type, we can use anything, P-type, N-type, or UMG. The cycle time for 650 kg is between 56 and 58 hours, which is exceptionally low. The energy consumption is below 7 kilowatt hours per kg. Argon consumption around 80 standard cubic meter per cycle. And the water flow rate for cooling is 130 liters per minute, with a variable inlet temperature between 15 and 35 centigrade. The growth speed can adjust it uniform between 5 and 30 millimeters, and as mentioned before, the interface shape is free adjustable. The yield data we got so far are a mass ingot yield of more than 74%. The usable brick height for a 290 millimeter total ingot height is between 230 and 240 millimeters. Due to the TMFs and the process tuning we can do with this furnace, a recycling ratio of more than 90% can be achieved. And this results in a virgin silicon consumption of less than 560 tons per 100 megawatt. The question now is what cell efficiencies can be achieved with this furnace. So here I would like to give you an example about multicrystalline dendrite growth, what we have done in our furnaces. You use localized cooling. For sure you have to spend special attention to the nucleation phase, and there is applied an initial lateral growth mechanism, and you have to maintain the original structure during crystallization process. This means the growth conditions and interface shape are quite important. Here you see you see an analysis which was performed by the Fraunhofer in Erlangen. It started with a grain size analysis where you get the number and the area of the grains, followed by a grain orientation analysis, and finally you get a grain boundary analysis. And as you can see, we have more than 60% of the grain boundaries are sigma grain boundaries, which results in a low defect density and a very high efficiency for the multicrystalline cells, and a very narrow distribution. As you can see, the median is between 74 and 76%, and it's a very tight distribution. What I would like to mention is that those results were achieved with a standard cell process, so nothing special in this cell process, and it's an industrial proven process. By further modification and adjustments, it might be possible or will be possible to drive the efficiency for multicrystalline cells towards 18% and above. But what to do if you need to have a solution on short notice? And this is, our answer to this is the mono-square process. The mono-square process is a new silicon nickelization process. It's an ALD patented technology. And I would like to explain the process sequences a little bit more in detail. You put on the bottom a mono seed plate or tiles, load above the poly chunks or the feed and the other feedstock, and then it's key that you maintain the seed plate during melting. Once you reach the seed layer, you switch over to crystallization, and then you grow mono material from the bottom to the top. After the finishing of crystallization and after the process cycle, you cut off the bottom of the ingot and use this bottom as a seed for the next crystallization. Therefore, it is quite important because the seed costs have an impact on the overall crystallization costs. It is quite important to reuse the seed as much as possible. For this, you must be capable to maintain the seed during melting process. Here it is shown the original loading of seed tiles in a Gen 6 crucible. Because you have to avoid crucible cracking, you have to stay away from the edges of the crucible. And here in this diagram is shown the melting down speed before start of crystallization. And you see in two positions, again, off-center and center position. And as you can see, in both positions, we achieve the same melting down speed, which is a key factor for maintaining the seed plate. Here you can see the bottom cut of a Gen 6 run, monocrystalline, as you can see here with the white line indicates the multicrystalline area, and anything in here is monocrystalline. So this means there's no problem to use those tiles as a seed for the next run. Let me now show some data from the monosquare process. For sure, for production, it is necessary that you have a high throughput. You need to have a reproducible monosquare process. You have to maximize the usable ingot height, and the C reuse procedure is key for success. And furthermore, in order to bring down the cost, there's always a goal to reduce the initial seed thickness. The cycle time we achieved so far for 650 kg charge is plus 4 to 6 hours compared with the standard multicrystalline process. The seed thickness we used was 25 millimeters, and we got a mono yield of above 80% for the total ingot volume. All 16 center bricks are full mono wafers, which equals 44%. Edge and corner bricks have multi-area in, and we call them hybrid wafers. So far, we experienced no increased inclusion levels. This means there was no impact on slicing behavior of those materials. The low lifetime zone in the bottom area is slightly increased, but surprisingly, it can be used for cell making, which means the lifetime is not a very good indicator for judging about the usable brick height for this material. So finally, we got similar ingot yields compared with multicrystalline material and an exceptional low cycle time, which means we were about 62 to 64 hours. Here I would like to show a little bit more about the different types of wafers you get within one ingot. As you can see, from the bottom to the top, you have an increased multi-fraction for the corner bricks. The center bricks stay mono, 100%, and even for the edge bricks, you have a slightly increased multi-fraction. This means you have different types of wafers within one ingot. Sometimes people say they remelt these hybrid wafers, but from our point of view, this is not an option. So you must get use of this material. Full mono is a target for the future, but the future will also show whether this is the right direction or not. What you need in any case is to have a classification tool at wafer level which can already predict the achievable cell efficiency so that you can make an automation in line. And we think here the photoluminescence is a key tool for the wafer classification. Wafer handling, sorting, and distribution is more challenging for this material, and for sure you need to automate this process. Now I would like to show what efficiencies can be achieved with a different type of wafers from this material. As mentioned before, you have a nucleation from the side walls, which cause a multi-area, and this multi-area determines the cell process. Because the market doesn't accept appearance problems, and If the multi-area exceeds a certain amount, then you have problems if you handle this material in a mono process. What we saw is a defect accumulation over the ingot height, which result in a broader distribution compared with a classical multicrystalline process. The average cell efficiency we achieved with this material was between 17.2 and 17.4%, which is comparable with standard multi-cells. The goal for the future will be to minimize or suppress the multi-area and to optimize the mono-multi interface. Here we have an example for cell results from the full mono wafers from the center bricks. They always show 100 direction. There is no or only minor deviation from 100 direction. It's less than 0.2 degree. And this means the appearance and processing of those wafers is equal to classical CZ cells, or CZ wafers. Here you see an EL, electroluminescence analysis of the wafers from different heights of the ingot, and as mentioned before, you see a slight increase in defect density, which results in a broader distribution. We use the alkaline etching for the full mono cells. It is a standard mono cell process. And the average cell efficiency we achieved so far was between 18.3 and 18.5%. 80% of the wafers are above 18%, and the top efficiencies are close to 90%, which is, in our opinion, similar to standard mono CZ material. For the future, we see here that the defect engineering by adjustment of growth conditions will be key to lower and suppress the defect generation and accumulation, and especially the thermal gradients and the traveling magnetic fields will play an important role for achieving this goal. Another approach will be using N-type material in order to achieve higher cell efficiencies. But for this is key that you are able to reduce the defect densities before. Now, I would like to show you our results of the cost of ownership calculation. We have just considered the crystallization process. The costs for auxiliaries and cooling water are included. Only direct related process labor costs, related labor costs were involved. The process cycle time is depending on the charge weight. We use pre-coated crucibles, and spare and wear parts are included in this calculation. As you can see, with 650 kg charge weight, you have an annual power output around 13 megawatt per furnace at costs of around 13 US cent per wafer. By increasing charge weight, you drive up this to close to 15 megawatt annual output, and the wafer crystallization costs go down to below 11 cent per wafer. So let me summarize this here. At a first glance, at 13 megawatt annual output per furnace at a cost level of below 13 US cent per wafer. This means only 8 furnaces for 100 megawatt required. Now I would like to summarize. The SCU 650 provides a very low cost of ownership for crystallization of silicon for photovoltaic. Either multicrystalline or mono square processes in Gen 6 size were demonstrated up to 800 kg. The SCU 650 flexible system is a flexible system which is designed to meet quickly changing market demands. This means if you have a need for high output, you can run the process in multicrystalline, and if you have a need for high efficiency you can run the process in for as mono-square process. The annual power output per furnace is between 13 and 15 megawatt. Our unique top, bottom, and side heater design provides the necessary thermal field for the mono-square process. And by application of different heat gate designs, variations in interface shape can be established. And that's even within one run. It is further optimization required to maximize the mono yield, and the wafer classification by PL gives a solution to handle different wafer types in production. The wafer classification by Lauescan offers a very powerful tool to understand about the growth condition and the impact on the product quality. Defect generation and accumulation mechanism needs to be understood better, and here we ask whether the VG criteria, which is standard use in the CZ process, is applicable.